Okay, good. So in this video, we're going to obtain quantum electrodynamics action by putting some conditions about transformation on Dirac action. So Dirac action governs the fermions, the laws of fermions. Okay, and if we act some global transformation on the spinors, such as this one, where psi goes to e to the power I lambda times psi, and psi bar goes to e to the power minus I lambda psi bar. Remember that psi bar is nothing but psi dagger gamma 0. Okay, then the transformed Dirac action will look something like this. So both this psi bar and psi, they get transformed, and then we get two terms here. Okay, so remember that for m, the second term, the exponentials will cancel each other, as the e to the power I lambda can simply pass through the m term, mass term. But also remember that in the first term, there is derivative, and since this lambda, the parameter in the exponential term, does not depend on position, it can pass through. Okay, and this derivative, which is nothing but dou by dou x mu, derivative with respect to position, it will only act on psi. So we get that the negative exponential and positive one, they will cancel in both of the terms. And so what remains is nothing but the original Dirac action. And so we say that the global transformation, the transformation which does not depend on position, since the lambda was simply a constant, this transformation leaves the action invariant. So we say that the such transformation is a symmetry of the Dirac action. But what about lambda being a function of x, the function of position in space-time? In such case, the transformation will be called as a local transformation, as it depends on the space-time position at each point. So the psi and psi bar transform something like this, where the lambda, the parameter, is dependent on position. So our transformed Dirac action becomes something like this. The S Dirac prime is, and so we write for in the place of psi bar prime and psi the transformed spinors as this. Okay, and now the key difference here will be that the exponential term will not simply pass through the derivative term as in the case of global transformation. So here we get two terms as this, and the exponential terms in the case of mass, the second term, will simply cancel, but in the first term we will get now two subterms. So derivative first will act on the exponential term and then on the spinor as this. Okay, so remember, the derivative of exponential of something will be written as the exponential times the derivative of that variable. So we get the exponential terms on the left times the derivative term of I into lambda of x. Since the derivative is acting only on psi, the exponential term gets cancelled, and so we write this term as psi bar I gamma mu del mu times psi. And so note that these two terms, the two underlined terms, form the original Dirac action. And so we get Dirac action plus an additional term. Okay, here also the exponential term will cancel, and what remains is only psi bar I gamma mu and the derivative term, which has derivative acting on the parameter lambda. And so note that when we demanded the local transformation on Dirac action, we get an additional term. So we want to know if is there any way that we can compensate for this additional term so that our action remains locally invariant. And indeed there is a way. There's a trick given as follows. So we build a new action which is a combination of Dirac action, and an additional term is there in the action which is compatible with the Dirac action. So we choose this additional term to be something like this: psi bar n. N is some quantity that we don't know how it transforms. Okay, so we just start with this, and further we demand the local transformation. We add the local transformation on this one. So psi goes to e to the power I lambda times psi, and psi bar goes to e to the power minus I lambda psi bar. Both this lambda are the function of position, so they are dependent on some local point. Okay, so the transformed new action can be written as something like this: the Dirac action, the transformed Dirac action. So from the Dirac action, the first part, we get two terms, where in the second term, the mass term, the exponentials will simply cancel as before. And then the additional term in the action will transform something like this. Now we're simply taking this n to be transformed as n prime. So again, the derivative term will give us two terms, once acting on the exponential and then acting on the spinor psi. And so the second term, the underlying term, gives us nothing but the Dirac action and an extra additional derivative piece, and with the n prime, exponentials with the n prime, they simply cancel to become like this. And our goal is to keep this transformed action S nu prime same as S nu, which is nothing but S Dirac plus this additional piece that contains n. So this can be written as the Dirac action plus this additional piece. Okay, and this is same as what we have obtained here. And so if we demand this, if they are same, then the first thing, the Dirac action term in the both these sides will cancel, and this underlying terms should be same as this piece with n. So this gives us a condition that looks something like this: psi bar n psi is equal to d for x psi bar I squared gamma mu, the derivative term, plus the psi bar n prime psi. And so this gives us information about how this n is getting transformed. Okay, so we can write n to be equal to minus of gamma mu del mu lambda plus n prime. So n prime can be given as this. So this is how n is being transformed. N goes to n prime, which is equal to n plus gamma mu del mu lambda. And if I say that this n prime was nothing but gamma mu n mu prime, and n was nothing but gamma mu n mu, okay, so then we can get rid of gamma mu's. Okay, and all that remains is nothing but n mu prime equals to n mu plus del mu lambda. So the new action that we built from Dirac action and an additional term will look something like this. And instead of n, we write gamma mu n mu, and this n will transform by this gauge transformation rule. And so we'll write this n in more familiar term in terms of the force potential A mu. Okay, so the S nu will be written as this one, the Dirac action part plus d for x psi bar gamma mu A mu psi. So I will make it look more like the Dirac action. I'll take the A mu inside this Dirac action term by doing this. Okay. And then the mass term, whole bracket psi. Okay. So I will take I gamma mu as a common, psi bar I gamma mu, and the inside will get derivative minus I A mu. Okay. And this term in the bracket, del mu minus I A mu, is usually called as the capital D mu. Okay, so that the new action will look very similar to the Dirac action. So what we have obtained here is a new action which has spinors as well as a gauge field. Okay, and the derivative term that was appearing in the first case now will be cancelled by the transformation of this gauge field, so that this action as a whole will remain locally invariant. And so finally we write the QED action as the addition of the new action that we just built plus a gauge invariant action F mu nu